Okay, welcome to Chapter 1, Section 5, Uncertainty, Accuracy, and Precision. Section 4 kicked it up a notch. Section 5 is going to do that again. It's going to get a little bit harder. We're going to be doing more math. But first, accuracy and precision. With accuracy and precision, we're talking about how good our measurements are. And we're talking about error, the ways things can go wrong. There are two different kinds of error, and therefore two different ways of evaluating our measurements for how good they are. Accuracy talks about how close our measurements are to the true value. And thus, the type of error we're looking at is called bias. So bias throws your measurements off consistently in one direction. Imagine you're throwing darts at a dartboard. You're trying to hit the bullseye, you're aiming for the target, but there's a breeze, consistently pushing your darts off to one side. Okay, that is a form of bias. And thus, the breeze is making your measurement inaccurate. And the way you counter bias, the way you take that into account and eliminate it, is through calibration. Calibration is when you measure a known value, and then you correct for the error. So if you're using a balance in order to measure the mass of something, well, you'd go ahead and measure something whose mass you already know. And then you just correct for the error, correct for the difference. So you take something that you know weighs 50 grams, put it on the balance, it measures 50.1 grams, you know that it's reading 0.1 grams too high. Most digital balances, it's easy enough. You just hit the 0/tare button and it does that for you. For an analog device, calibration is a little bit more difficult. It means you have to take the measurement and then write down the error and remember it yourself. The other thing that we look at is precision. Okay, how closely grouped your answers are to one another. And you want a nice tight grouping. You want to get consistent answers. If your answers are scattered all over the place, if you're getting imprecision, if your measurements are imprecise, it's because you have a lot of noise. Okay? Think about it, you're at a party, you're trying to hear someone, you're listening. That's the signal. The person you want to talk to, the person you're trying to listen to, that's the signal you're trying to get. The other people at the party, they're just noise. Okay, that's information you don't want, messing with the signal. So that's why we used noise to talk about this kind of error, because it scatters the information all over the place. Instead of getting a consistent push in one direction, noise sends your information all over the place. It's random. Noise is more difficult to correct for. There are two ways of dealing with it. First, you can try to isolate your signal. So if you were trying to take the mass of something that has a very, very low mass, you're trying to measure in the micrograms or nanograms, that's difficult, but possible. What you would do is you'd put your balance in an isolated location, a glass box with sliding doors. Okay? They actually make those. And that way, you put your thing on the balance, you close the sliding doors, you don't have to worry about breezes constantly jiggling the pan. Another way to deal with noise is just to take lots and lots of measurements. Because the noise is random, it'll be all over the place, and you can average it out. That's how you get your signal to noise. So, what you're trying to do is trying to decrease the amount of noise and increase the amount of signal, so that you get a good signal-to-noise ratio, as they call it. So one way to increase the signal is to just take lots and lots of measurements. Another way is to actually find ways to increase the strength of the signal. Okay? But that varies depending on what sort of thing you're measuring. So, those are the two ways your measurements can be good or bad. Talking about accuracy and precision, bias and noise. Which means that, you can basically have, 4 different situations. Your measurements can be both accurate and precise, always tightly grouped right on target. Or they can be precise but inaccurate, in which case they're tightly grouped but they're off target. Consistent bias, low noise. Conversely, they can be accurate but imprecise. Okay, they're centered on the target, but they're widely scattered. Lots of noise, no bias. Or, worst of all possible worlds, inaccurate, imprecise. Plenty of bias, plenty of noise. You definitely don't want that. So, these are different ways your measurements can be good or bad. Okay, different ways errors can creep in. We always try to take those into account. We always try to deal with them. And a lot of the arguments scientists have is saying, are you getting some sort of noise or false signal in your measurements? Yep, scientists. Great big nerds. I love them. All right, that'll do it for this video. See you next time.